Right, so next we've got the concept of norm and distance as it relates to the inner product. So we looked at the norm and distance functions previously as they relate to the dot the dot product. So you can do the same for the inner product. In general, you can define norm and distance in terms of inner products in general. So if V is a real inner product space, then all the norm is, or the length of a vector with respect to that inner product, is simply just defined as you take the inner product of the vector with itself. That we know that's a quantity bigger than or equal to 0, and you take the square root of that, and that's the norm. Then the distance between two vectors is simply defined as the norm of the vector u minus v, and we know what the norm is in terms of the inner product. Right, and the norm of that vector is simply the inner product of u minus v with itself, and then you take the square root of that, and that's defined as the distance. So you can also define norms and distances in general with respect to different inner product operations. As long as the operation is the inner product, we can define the norm and the distance in this particular way. Now again, a vector of norm 1 is called a unit vector. Right, this brings us to theorem 2, which states that if you've got u and v, if u and v are vectors in a real inner product space V, and k is a scalar, then the norm is always bigger than or equal to 0, with equality if and only if v is the 0 vector. Then you've also got this scalar multiple property of the norm, and that is just the absolute value of k multiplied by the norm of the vector. And the distance between u and v is always the same as the distance between v and u. And the distance between u and v is always at least 0, with equality if and only if u is equal to v. Now if we look at how the norm is defined, and remember that, recall that the inner product of a vector with itself is always bigger than or equal to 0. And so that's going to imply that the norm of v is always bigger than or equal to 0, because the square root of a bigger than or equal to 0 number is always bigger than or equal to 0. Now, if the norm of v is 0, right, that happens. That's going to happen if and only if the inner product of v with itself is equal to 0. And we said by the axioms of the inner product, the only way that is the 0 is if v is the 0 vector. Okay, so this implies that the norm is 0 if and only if v is the 0 vector. So that takes care of the first property. Right, now if you look at the norm of the scalar multiple of v, that is defined by definition as that, and that you can actually observe that according to my axioms, we can write that as k times the inner product of v with the vector kv. And again, we apply the previous theorem we did, which then we can basically go and replace that with with k times the inner product of v with v. Right, so that is going to be the square root of k squared v with v. And that you can simply just replace that with the absolute value of k, because the squared makes any negative k positive, and So the square just basically takes k and it makes it positive. Okay, so that we can then replace that with the very end with what we want it to be. All right. Then the distance between u and v is the same as the distance between v and u, and the reason that holds is simply because, remember, we said the distance between u and v is the norm of the vector u minus v, and that we said is the square root of the inner product of u minus v with itself. Okay, and also if you look at the distance between v and u, that is going to be the norm of v minus u, which we know is going to be the norm of minus u minus v. Okay, and we know that by this little rule here, that is going to be the absolute value of minus 1 multiplied by the norm of u minus v. And the absolute value of that term then there becomes that there. Okay, and that is the distance between u and v. Okay, so the distance between u and v is the same as the distance between v and u. And then the last one is the distance between u and v always has to be positive. Well, one can actually, why is that? Because the distance between u and v, we said, is this norm here, and the norm by definition is always positive. And the only way that, if we just clean the slate, the only way that the distance between u and v is exactly equal to 0, the only way that can happen is if the norm of this vector, the norm of this vector here, the vector u minus v, is equal to 0. And by the first property here, a norm is equal to 0 if and only if the vector itself is the 0 vector. Okay, and that happens if and only if u is equal to the vector v. Right, so those properties are very easily verified. Right, so let's look at the following example. There they ask us to consider that inner product that we've defined previously on M22. Okay, so we're given u and v, and they just ask us to show that what is the inner product of u with v. And that by definition is pretty much, it's just the trace of the matrix U transpose, which is pretty much going to be 1, 0, 2, minus 1. And we're going to take the product of that with V, which is minus 2, minus 1, 1, 3. Okay, and if we are to work out the trace of that matrix, so taking that to the side, we multiply the two 2x2 matrices out, and what's the trace of that? The trace of that is minus 7. Okay, so that's just a little exercise there. What's the norm of U? The norm of U is going to be defined as, it is basically, it's going to be the square root of the inner product, so if, of U with itself. So let's look at what the trace is of that. That is going to be, it's going to be 1, 0, 2 minus 1. Okay, and then the trace of that is going to be the trace of multiplying that out. Okay, so it's the trace of that, which is simply the sum of the diagonal entries, which in this case is 6. Right, so the norm becomes, okay, so the norm then becomes, the norm of u becomes the square root of 6. Okay, then what is the distance between u and v? So the distance between the vector u and v, that is going to be, by definition, the norm between the vector u minus v. Okay, and the norm of, well, first of all, the vector u minus v is simply defined as the matrix 1 minus 2, then it's 2 minus 1, okay, and then this entry here, that's going to be minus 1, and then it's minus 1 minus 3, which is minus 4, and so that is going to be the 2 by 2 matrix 3 minus 1 minus 4. Okay, so we need to go and find the norm of this vector u minus v. So essentially what we need to do is we need to go and find then the inner product of u minus v with itself to right, and that is going to be pretty much, it's going to be the trace of the first vector transpose, and that is going to be the matrix 3 minus 1, 3 minus 4, and then you're going to multiply that with the vector itself, which is 3 minus 1 minus 4. Okay, and calculating the trace of that matrix is not a difficult thing, so multiplying out. Okay, and the trace of that is simply 35. Right, so then now it's easy to go and compute the actual norm. So the norm is going to be of u minus v. It is going to be the square root of 35. Right, so next is example. Consider the evaluation in a product, and your sample points are given as minus 1, 0, and 1 respectively. So now we are asked to find the inner product of P with Q, and then the norm of P and the distance between P and Q. And I'm going to do this very quickly. So what is the norm, or what is the inner product of P with Q? That is going to be, it's going to be, as I said, it's going to be P in the point minus 1 multiplied by Q in the point minus 1 plus P in the point 0 multiplied by Q in the point 0 plus P in the point 1 multiplied by Q in the point 1. And then just quickly go and work that out. What's P in the point minus 1? But that's 4. And what is Q in the point minus 1? That's going to be 3 minus 1 squared. Minus 1 squared is 1. So 3 minus 1 is 2. So that's going to be that. What is P in the point 0? It's going to be 2. What is Q in the point 0? It's going to be 3. And what is P in the point 1? P in the point 1 is 2 minus 1 plus 1 squared, which is 1. So that is going to be 2. And what is Q in the point 1? It is 3 minus 1, which is 2. Okay, so that then becomes That becomes 18. Right, so not difficult to do. Then, what is the norm of, what's the norm of P? The norm of P is pretty much, well, what do we need to determine first? We need to determine the inner product of P with itself. And again, by definition, that's going to be P in the point minus 1 multiplied by P in the point minus 1, which is P in the point minus 1 squared. Then again, we've got P in the point 0 multiplied by P in the point 0, which is P in the point 0 squared, plus P in the point 1 multiplied by P in the point 1, which is P in the point 1 squared, and that is going to basically then be, what's P in the point minus 1? That's going to be 4 squared. What is P in the point 0? It's going to be 2 squared. And what is P in the point 1? 2 minus 1 plus 1, which is 2 squared. Okay. So that's 24. And so what is the norm of P? The norm of P is going to be the square root of P's inner product with itself, and that is going to be the square root of 24. Right, and then the distance between P and Q, that is also not difficult to work out. To do that, we need to find the inner product of P minus Q with itself. Okay, and so that is going to be, by definition, it's going to be the function P minus Q within the point minus 1, and then you're going to multiply that with the function P minus Q in the point minus 1, and that is going to be that function in the point squared. Then you're going to have the second one, you're going to have the function P minus Q in the point 0 multiplied by the function P minus Q in the point 0, so that is going to be that squared, and then you're going to again have the function P minus Q in the point 1 multiplied by the same thing, which is going to be squared. And now we need to go and work out the difference between the function P. What is the difference? What is P minus Q? It's basically the function formed by taking that and from that subtracting that in each point. Okay, so P minus Q in the point minus 1, that's going to be the function P in the point minus 1 minus the function Q in the point minus 1. So that is going to be 4 minus, now the Q part, where Q is in minus 1, that is going to be 2. Then we're going to work out P minus Q in the point 0, so that is going to be the function P in the point 0 minus the function Q in the point 0, which is 3. And then lastly, we've got P in the point 1, which is 2, minus the function Q in the point 1, which is also Q in the point 1 is 2, right? So that is going to be 2 minus 2 squared, right? So that is going to be 4 plus 1, and that's going to be 5. Okay, so that is what is the actual distance between those two vectors? Calculated that as 5, and so the distance is going to be the norm of the vector P minus Q, which is going to be the square root of which vector, or not vector, of which product. It's going to be the product that we just calculated. It's going to be that thing there, and so that is going to be the square root of 5. Okay, so that is how this evaluation in a product works. That is the norm or the distance in terms of this evaluation in a product. Right, just one more example. Let's look at Consider the weighted Euclidean inner product where the weights are 2, 1, 3 respectively, and the two vectors u and v are given, and we just quickly asked to calculate the norm of v. So the norm of v, we said, is the product, the inner product of v with itself, and in this particular, well, it's the square root of that. Okay, so basically, what we're first going to do is let's just calculate that product there, and that product there is, again, by definition, it is the it's basically it's the dot product of v with itself, but then you introduce the weights. So it's basically going to be 4 times 4. Okay, and then separately you're going to have 1 times 1. And then you've got your other terms 0 times 0. Okay, and then you have your weights. That's going to be your first weight. That's going to be your second weight. And your third weight is going to be 3. So working that out, we get, that is 32 plus 1, and that's going to be 33. So what is the what's the norm of v? The norm of v is going to be the square root of this thing that this inner product that we worked out, and that is just going to be the square root of 33. Okay, then what is the distance between u and v? To get the distance between u and v, we need to look at what this inner product looks like. U minus v with u minus v. So that is going to be firstly, what is u minus v? If we are to work out u minus v, that is going to be 1 minus 4, which is minus 3. That's going to be minus 2 minus 1, which is minus 3. And it's going to be 1 minus 0, which is 1. Okay. Now what you're going to do is you are going to take the dot product, well, not the dot product, the inner product of u minus v with itself, and basically doing this, you're going to have minus 3. Okay, so working that out, we take that there, and that is then going to be, first of all, let's put the terms together first. So that's minus 3. It's going to be minus 3 times minus 3. That's the first term. Then it's going to be minus 3 times minus 3. That's the second term. And then it's going to be 1 times 1. And that's the third term. And then introduce the weights. First weight is 2. The second weight is 1. And the third weight is 3. Okay, and then adding all of that up, we get, okay, and that is going to be 30. So the distance between u and v is simply going to be, it's going to be the square root of what? It's going to be the square root of this inner product that we worked out, which is that thing there, and that is simply going to be the square root of 30. Alright, so in terms of the weighted Euclidean inner product, that is how the norm and the distance basically is going to look like. Okay, now just this little last section here on matrix inner products. If u and v are vectors in Rn that are expressed in column form, and if it's given that A is a square n by n matrix, now if u dot v is the Euclidean inner product on Rn, then this inner product, defined as follows, is you pretty much take the column vector formed by that multiplication there, and you take the column vector and you take that, and you take the inner or you take the Euclidean inner product, the normal dot product that we've come to get familiar with, then that you can just write that as pretty much it's the transpose of the column vector, which becomes the row vector, multiplied by a column vector, and that can just be written as the transpose of the vector V multiplied by the transpose of the matrix A multiplied by U. And this particular inner product, that is called the inner product generated by the matrix A. So that's just a little definition. So in this example here they show say that we need to show that the inner product generated by A, we need to show that that is basically given by that, where A is the defined matrix, the diagonal matrix. So that is not terribly difficult to show. It's simply an application of the way that this inner product is defined. So if we have to quickly look at that. Okay, so now we've got right, so we've got the matrix A. Right, so we've got the matrix A, the diagonal matrix A, and we are going to multiply that with our first column vector, which is U1, U2. Okay, and we are now that is going to be a column vector, and that's going to be the column vector. Our column vector is going to look like, and then if we take the matrix A and we go and multiply that with the second column vector, which in this case is my V vector, that is definitely going to be, again, it's going to be the same story. It's 3V1, 2V2. Right, so what have I calculated? That and that part there. Okay, now that you can pretty much write as, so we're going to, by definition, then take the dot product, the traditional dot product with the second vector. In this case, that is there, that vector there, and that is just going to be 9 U1V1 plus 4 U2V2. Okay, so that's just illustration of how this this particular inner product how it works. The second one is use the inner product to compute the inner product of U with V if it is given that U is the vector -3, 2 and V is the vector 1, 7. Okay, so that is not, again, that is not a challenging thing. So we just pretty much use this product that we worked out, which gives us the inner product of U with V. Okay, so basically that is just the inner product of U with V is now just basically going to be, it's going to be 9 U1V1, which is -3 and 1, so that's -3 and 1, and you're going to add that to 4 U2V2, which is going to be 2 and 7. Okay, and that becomes, okay, and right, so that is going to be that's going to be 29, right? Okay. All right, so that's matrix inner product, and then the last little problem, just throwing everything together. Here they just ask us to compute, given that the norm of U is 1, the norm of V is 2, and the norm of W is square root of 3, and inner product of U and V is -1, inner product of U, W is 0, and the product of V with W is 3. Just compute that. Just compute that vector there. Now again, this is just an application of what we've done up until now. So again, you can basically just write that as so we just repeatedly we apply the axioms, so that's going to be 2u minus v, okay, plus we can replace that with w, 2u minus v, and then again that one we can replace with v, 2u, v minus v, and that we can replace with w, 2u, and we can replace that term, the other term, and we get that that's going to be minus v, and then using using your axioms, basically that just can be written in a neater way. That's going to be 2vu, and again that's going to be minus v, and that's going to be 2 wu, and that is going to be minus wv, and just to write this in a more familiar form, that's going to be 2uv. Again, it's just repeatedly the same axiom that I'm working out, that I'm using, and that's going to be 2uw minus vw. Okay, so we know what the inner product of u with v is. The inner product of u with v is minus 1, so that is going to be minus 2. The inner product of v with itself, remember what we said, what is the norm of v? The norm of v is the square root of the inner product of v with itself. So what is the inner product of v with itself? It is basically the square of the norm of v is basically going to be the inner product of v with itself. So what is the square of the norm of v? That is going to be 2 times 2, which is 4. Okay, and then what is the inner product of u with w? It's 0. And what is the inner product of v with w? That is going to be 3. Okay, so that is going to be minus 9.